PCS members and friends to our today's Tuesday PCS IBS seminar. Today we have with us Professor Tero Heikkilä, and it is a great pleasure to have him here with us. And I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Okay, thank you, Tilen. So it's our pleasure to have Tero Tapio Heikkilä, professor from University of Jyväskylä, today with us. So he'll be talking about flat bands and topological polarization. So I hope you remember he was also giving a talk at our flatband workshop in August this year. And so we now would have an extended version of that presentation and perhaps new things. So let me briefly introduce Tero. So he received his degree at the Helsinki University of Technology in 2003. And then moved as a postdoc to University of Basel and later to he moved to Aalto University, where he stayed for quite some time, first as a postdoc and then as a theory group leader. And since 2013, he's a professor at the Jyväskylä University, where he's interested broadly in condensed matter theory, in various aspects like superconducting magnetic heterostructures, topological media, non-equilibrium physics, thermoelectricity fluctuations, and as the title suggests, flat bands. And so with this, Tero, please, the screen is all yours.
Thank you, Alexei, and thanks for the very nice introduction. And obviously, it would be a great pleasure to be actually, it would be very nice to be there, but let's say this is the second best option now. And since I cannot come there, I want to show how it is like in Jyväskylä. When I think when August I gave this talk, I showed the picture, the summer picture of Jyväskylä. Now I show a winter one. And the reason is that we already have actually snow here, and sort of everything starts to be white, which is quite good. It doesn't necessarily have to be like that at this time of the year, and without snow it would be pretty dark. So this is I'm actually in this building right now. I think roughly this window here, and this is Jyväskylä. And okay, I crossed this bridge over the frozen lake this morning to come to work. So as Alexei mentioned, I already gave a talk at the IBS meeting in August on flat bands, and there I concentrated on sort of how to create different types of flat bands in graphene-based systems. Here, actually, in this talk, I will take a different perspective, and I will talk about a concept called topological polarization. And then it's linked to flat bands. And this sort of work that I will talk about is mostly covered in these two papers that I list here. Okay, and the work has been done together with sort of Grisha Volovic and Jaakko Nissinen from Aalto University. With Grisha, we have worked on these flat bands already for a bit more than 10 years now. And then part of the work was done with Timo Hyörtä and Risto Järvi. Risto is my PhD student who is about to finish his PhD, which will be very nice work, and he might be looking for a postdoc. Let's see. And so this is a hint. Okay. Now this is basically the contents of my talk. I will actually focus a bit on topology here, and point out that you can construct topological actions sort of in a way that includes something that about the crystalline matter, so-called elasticity tetrads. And here we consider these tetrads as dynamical fields. And then once we have done this consideration, we notice that actually there are new types of topological insulators that one can describe with the notion of this action. So besides the usual quantum Hall effect that you might have in topological insulators, you have this sort of polarization, quantized polarization jump in in the 3D TIs. I will explain these pictures later in my talk. And I will show a model system which shows a transition from a nodal line semi-metal phase, which has small surface flat bands, to a topological insulator phase, which has large flat bands at the surface. And then also they also have this surface polarization, which is kind of a sort of denotes the presence of this non-trivial topology in these systems. And towards the end of my talk, if the time allows, I will take another view on flat bands and show how interactions can lead to band flattening in a certain model. And I briefly discussed a recent paper on twisted bilayer graphene related with that. And by the way, if you have any questions, please stop me during my talk. I'm happy to discuss any of the details. Some parts will be a bit formal, and I hope to be able to sort of cross them without losing part of the audience. Let's see. Okay, let me start with something which I think I saw already in August, sort of something simple where we kind of want to classify electron spectra at first on the level of the sort of energy spectra. And what we know that in sort of crystalline matter, we can, let's say, the most typical examples of electron spectra are the band insulators and metals, where the Fermi energy is inside the conduction band, and where the majority of the physics happens sort of around the Fermi surface. Let's say the low energy physics, like transport phenomena. And then we also have this sort of type of semi-metals, Dirac Weil points, where we have a band crossing. And then so we can start from this band crossing and extend it into a flat band. This would be an ideal flat band, which is now connected to continuum, or we could also create a flat band which is sort of just flat and not connected to anything. This is kind of in a way ideal, where it's completely flat, this band. In practice, probably it is hard to realize this, and rather actually you have these flat bands with a finite bandwidth. So here is an example of one such flat band, and here's another one. This picture shows here the flat band in magic angle twisted bilayer graphene, and it does have a finite bandwidth. It doesn't show up too much in this picture, but besides this sort of bandwidth, there is another characteristics of the flat band, which is the flat band area in moment to space. So it's the extension of the flat band in the moment to space, which I call this omega flat band. Okay, so let me show this just sort of as examples. So in my talk in August, I'm not expecting that you remember my talk, but I just want to I don't want to repeat too much of that talk. I sort of covered three types of flat bands. So perically strained graphene, which had a sort of this type of flat band dispersion, and then twisted bilayer graphene, which I already showed, and rhombohedral graphite surface, which had another type of flat band. And sort of these are just examples of this phenomena that I showed you in the schematic pictures. One motivation that to study flat bands is that they host this sort of correlated electron states. So what I showed in the previous slides, it was kind of an example of non-interacting electron dispersions. And the interesting question is that what happens if you add interactions? And interactions are known to lead to spontaneous reciprocal symmetry states, phase transitions to states like superconductivity or magnetism, where now the characteristic property would be the critical temperature, the temperature at which this order takes place. In the case of superconductivity, for example, the TC on sort of typical Fermi level systems behaves like this. The TC is proportional to some cutoff energy times the exponential of -1 over the coupling constant times the density of states at the Fermi surface. Now, if you want to increase TC, what you might like to do is either increase the coupling constant or increase the density of states. So let's assume that you cannot increase the coupling constant. So let's the way to get a higher DC is to increase the density of states. And the extreme limit of increasing this density of states is the flat band. Okay, and we cannot, of course, from this picture argue what happens in the case of flat bands. Actually, we have to start from the flat band and study what happens to the TC. But in this extreme limit, we get basically that the TC goes linearly with the coupling constant, but sort of in such a way that this coupling constant multiplies actually the size of this flat band. And this law holds if the TC calculated this way is larger than this bandwidth of this flat band. So if let's say the TC would be larger than this intrinsic delta E, then this is more or less correct.
Professor Heikkilä,
yes.
We have a question from Alexei.
Okay. Yes, please.
Yeah, a simple. So I just want to be sure. So here, when you're talking about the flat band surface, that's basically the part of the Brillouin zone that is flat. That's what you mean here.
Yes.
Okay. Thanks.
Yeah, exactly. Yeah, thanks for the. Okay, so this will hopefully become clear that this is this omega, but it's indeed you kind of. I think it's a kind of a self-consistent criterion. You have to define sort of how many states are within a certain energy interval. For example, this would be the number of states within this energy interval. That would be the size of the flat band. Okay, but anyway, in order to sort of now, if we look at these expressions, in order to maximize TC under these constraints, what you would like to do is to maximize this omega and minimize delta E. And this is kind of the motivation in my talk to do. So how to make larger flat bands, how to make them more flat. And in the case of the examples that I mentioned already earlier, we have studied these three types of sort of flat band creation in graphene-based systems, and I can kind of enumerate the size of the flat bands in these systems. So in the case of sort of ABC stacked graphene, the size of the flat band sort of scales with the square of the size of the sort of interlayer hopping constant divided by the Fermi velocity. Okay, and you will see later in my talk that this actually is a fraction of the sort of entire Brillouin zone of the original 2D system. In periodically strained graphene, so what you do is that you sort of put strain in some way, and then you vary the strain over some length, and this can be described by a pseudo vector potential sort of this strain and pseudo magnetic field, and kind of which oscillates as a function of position. In this case, you may get a flat band for large enough oscillations, and the size of the flat band is actually essentially this amplitude of the pseudomagnetic field, which actually happens to have the scale of 1 over length squared in power units. And in the case of twisted bilayer graphene, which is now sort of maybe the best known example of flat bands, which has been studied in many places, the size of the flat band is basically equal to the size of the Brillouin zone of the superlattice. So for those who might not know twisted bilayer graphene yet, you have these two graphene layers, you twist them with respect to each other, and you get this moire pattern. And the moire pattern is another lattice. which has a sort of kind of a large lattice constant, which then means that the Brillouin zone size is smaller. So the kind of, here's an example of the kind of the superlattice Brillouin zone that is constructed from the two Brillouin zones of the two graphenes. And in this case, the superlattice Brillouin zone is basically its size is the graphene Brillouin zone divided by the number of atoms inside the unit cell of the one sort of Moiré period. And in order to get the flat bands in this bilayer graphene, you have to twist to a so-called magic angle, which actually depends on the hopping between the layers. But for the sort of practical case that you have in graphene, this magic angle is 1.1 degrees, in which cases n is 10 to 4. So the message in this slide basically is that you can create flat bands in these systems, and they actually do show already interesting correlated states. All of them have been shown to show such interesting correlated states, but the typical sort of critical temperatures of those systems are on the order of a few Kelvin. And I'm claiming here that the reason for this low temperatures is the fact that the size of the flat band is small. So in order to increase the TC, we would like to increase the size of the flat bands. Okay, so before I get there, let me start from another type of classification of electronic matter, which is that of topological classification. So here is a sort of example of the zoo of topological media that we now know. Actually, many of the pictures are based on Krzysztof Wolovic's book, The Universe in a Helium Droplet. And then some of them were added later in our work, 2011. So what we now know is that topology is a way to sort of characterize robust features in electronic spectra, and this can be done for various types of topological media. In fact, already the Fermi surface that I mentioned before has also a topological charge, which sort of prevents it from forming a gap under small interactions. And this is why we can actually do even sort of theory of metals. But then we have also these Dirac points that were mentioned, or Weyl points, which are now these hedgehogs in momentum space. I will probably not explain the picture if you don't know what it means, but okay, it's good to try to find out. Now, in the case of 2D, there are the topological insulators, which actually are skyrmions in momentum space. So that is a sort of type of defect as well. And then there are some other sort of more complicated topological media, such as actually there is a topological classification of some certain type of flat bands, and then also this sort of Fermi arc states. I will discuss in my talk mostly about something that was not so much mentioned in Krzysztof's book, which is the Dirac line materials. I think there are some Dirac lines actually there, but anyway, and I will show you how to sort of characterize these Dirac line materials and how they actually are connected with the flat band physics. Okay, now one thing that these topological media have in common is that they two things actually. They have protected the surface or edge modes, and they have this sort of response tied to their topology. Okay, topological response is typically something that does not show up in the equations of motion, but it shows up in the sort of entire response. So examples for 3D are these wild semimetals which have the chiral anomaly and Fermi arc surface states. In the case of topological insulators, I'm not sure, by the way, if the Skyrmion is the right picture for this, but anyway, but topological insulators have the quantized Hall response or spin Hall response. In my talk, I don't make a difference between the spin Hall and the sort of charge Hall response. I'm kind of assuming that the fermions are spinless. But anyway, the topological insulators also have this so-called half Dirac surface states in 3D. And then there are these Dirac line materials, which are basically Dirac lines are sort of systems where you have this Dirac crossing in 2D, and then you extend it to a third dimension by kind of continuing this crossing, sort of band crossing to a line. And sort of before our work, I didn't quite know what would be the topological response in these systems. But what I did know is that they have this flat band or drumhead surface states, these nodal lines. Okay, first let's look at the sort of this whole response of these topological insulators, and I point out one kind of detail which is linked to the scales in this. So we want to quantize the conductivity in these systems, and in 2D the conductance scales like conductivity times the width divided by length. So this combination is dimensionless, which means that the conductance has the same dimension as, let's say, conductivity has the same dimension as conductance. And we know that conductance always has a dimension of Siemens, which you can get from a combination of sort of natural constants is E and H. So in 2D, since the conductivity has the same dimension as conductance, it can have the dimension of E squared over H. Okay, and then you can talk about quantized sort of response shown in conductivity, quantized in the units of E squared over H. In 3D, the conductivity scales differently because the conductance is now area divided by length. So this has a scale of length, which means that the 3D conductivity has a scale of this sigma 0 divided by length. So if you have quantized response, the question is, what is this L in the quantized response of conductivity? Okay, now I give you the answer immediately. This was already noticed by Hartree in 1987, that in the case of quantized response of 3D media, you have to actually multiply the fundamental constants by a reciprocal lattice vector. And reciprocal lattice vector of the crystal that has this dimension of inverse length, which provides this kind of missing L here. At the same time, it shows that you cannot have, I mean, you wouldn't be able to have a sort of 3D topological insulator response in continuous media. You need this sort of lattice to support this. Okay, and with this notion, I kind of started to ask how to build sort of a consistent theory of quantized responses in topological media. And here I follow basically my co-authors, Jaakko Nissinen and Krista Volovic. They sort of realize that you can actually construct topological actions which have dynamical fields related to the crystalline media if you add a certain type of gauge fields. And now that this couple of slides are pretty formal, so I'm sorry for that, but I will hopefully can get to a bit less in a moment. But basically, the idea is the following. So we want to describe the crystal lattice via some sort of gauge fields. And so let's first assume that this crystal lattice is perfect. So it is characterized by some reciprocal lattice vectors. I mean, it's also characterized by lattice vectors, but then in particular, it is characterized by reciprocal lattice vectors K. There are 3 of them for 3D crystals. Now we can define these phase functions, which are just sort of this reciprocal lattice vector K dot R in the absence of deformations. Okay. And using these phase vectors, we can define so-called Bragg planes, which is basically these Bragg planes are the coordinates are satisfying the condition where this phase functions are equal to 2 pi n a, where n is an integer. Okay, so now we have this let's say 3 sets of Bragg planes for sort of different x functions. So there are three of them. And then we look for the intersections of the different Bragg planes. And what we find is that these are the crystal lattice points. Okay, so this may sound like a complicated way of constructing the crystal lattice, but if you do this, you can actually sort of describe also a crystal lattice with deformations, such as this one. In this case, you would add some deviation to this phase function, but this lattice condition would remain the same. Okay. Now, so now you could imagine that this X could be might be sort of suitable field to describe your crystal lattice, and it kind of is. But the problem is that it has this 2 pi periodicity. You add a 2 pi, and you get the same response. So, but this is kind of similar to, it's kind of a U1 gauge field in this way. But rather than this X, actually what you want to do is to describe these derivatives of these phase fields, and these derivatives don't have this 2 pi periodicity issue, and sort of these derivatives are called elasticity tetrads, and they kind of behave the same way as vector potentials of the electromagnetic theory. So in the case of no deformations, actually these elasticity tetrads just coincide with the reciprocal lattice vectors. But in the general case, they are a generalization of those reciprocal lattice vectors to allow for both deformations in space and time. So they can be dynamic. Okay, so once we identified these elasticity tetrads, and they are kind of them as kind of vector potentials, they can actually have a field in the same way as vector potentials can be characterized by a field strength tensor. Also, these elasticity tetrads have a field strength, which is actually torsion of the lattice. And in fact, sort of the lattice which is deformed, it can be strongly deformed, but if it doesn't contain any dislocations, this torsion has to be 0, and this is an extra condition for the constraint for this sort of elasticity tetrads. Okay, so now let's take these elasticity tetrads and the real vector potentials and try to construct topological actions, which are scalars, from these fields. And especially we sort of emphasize the fact that they have a dimension of 1/L length in both cases. Alexei, you have a question.
Yeah, again, a simple one. So the torsion, well, basically the EIAs, do they satisfy the usual Maxwell equations in the end? So are they really full analogs of the vector potentials, or there's a difference still?
No, I think, I mean, they would satisfy some elastic media equations. But it's in the same way Maxwell's equations sort of, I mean, inside the media are of course look different. So I think there would be some own dynamical equations for E, which you could actually derive from the actions that I'm presenting in principle. We haven't done it, but I think in principle you should be able to do that.
Okay, thank you.
But one thing maybe to mention here is that you can construct the effective metric from this elasticity tetrads. So the metric, local metric, is a square of these tetrads. If you are more interested in how they behave, this first paper here has information on how this metric is constructed from there. So you can, in principle, have kind of gravity. You can study kind of gravity effects in media by changing metric. Okay, so we want to construct a topological action from which we get kind of quantized responses. And okay, so maybe actually I should first mention how you do it in 2D media. So you have a Chern-Simons action in 2D media, which looks like this. So you have an action that depends only on the vector potentials, and you sort of construct it so that it's completely isotropic. So changing the rotating space doesn't change this action, or rotating space or time. And it contains this topological invariant n, which describes whether you have topological response or not. So this is an integer quantity. And what you notice is that you have to integrate over space and time in here, which is kind of like integrate over three coordinate. And so therefore the dimension of this sort of integrand here has to be it should be 1 over L the cubed, not L cubed, but 1 over L cubed. Okay, but this shows that you can do it with this action. So, and once you have that action, you actually I will discuss in a moment how it describes actually quantum Hall effect, the quantized Hall response. Now, simply based on dimensional analysis, we cannot do exactly the same thing for 3D, because indeed this scales like 1 over L cubed, but now in 3D we would like to integrate over 3D position. So we would have to get an additional field here that also scales like 1 over L. Okay, and the additional field is the elasticity tetrad. Okay, so now the corresponding action for 3D media is like this. So you have the same vector potential times the derivative of vector potential here. This is the fully antisymmetric tensor, and this is the elasticity tetrad and its component that I described just above. And now what you can notice is that now you have this 4-dimensional integral here, and so the remaining term has to be 1 over has to scale like 1 over L to the 4th power. There is a topological charge here, which can be described in terms of the Green's function. And the important thing for the topological charge here is that this momentum integral here goes over the 2D boundary of the 3D reciprocal lattice unit cell. So there are 3 topological charges in principle. I will give you a chance for asking in a moment. I just explained this again. So there are three charges in three directions, and this integral every time goes over the the area in sort of the 2D boundary of the 3D reciprocal lattice unit cell in the direction indicated here. So kind of like for the N3, for example, you would integrate over the surface spanned by the E1 and E2 fields. Okay, and remember, for undeformed media, these are the reciprocal lattice vectors, so they actually cover the Brillouin zone. Okay, now question.
Yeah. So you want to claim this term is a topological, right?
Sorry?
So you want to say this action is a topological action?
Yes, yes, it is a topological action.
But by definition, topological action should be invariant under the change of the metric, right? But in your case, you have in front coefficient elasticity, which is multiplied in your action. So I think if you change your metric, then action is dependent. So how does that?
I think you have to define your metric correctly. So like I said, this elasticity, okay, this is this is part where I have to do guesswork. You actually have to check this paper for this. So but as far as I understand, this just implies that you actually have to redefine your lattice metric in a proper way to get there.
Isn't elasticity a function of your metric? No. What do you mean by you?
No, it's the other way around. The other way around. The metric is a functional depends on the elasticity.
So what do you mean by you redefine your metric?
So
they are the function of each other. So if you change metric, elasticity changes.
Well, the other way around. So if you change the elasticity, the metric changes. So in lattice media, you describe the distances between distances in terms of the number of lattice sites.
Mm-hmm.
And now if you deform your media, you also kind of change the way how you define those distances. So this is what I'm saying.
Okay.
So I think this is the answer to your question, but okay, I'm on a weak ground here because I'm not. But okay, I think this is discussed in more detail here.
Okay, thank you.
Alexei has a question.
Yeah, well, a quick, maybe trivial remark to the previous question. If I remember correctly, the E is defined as basically the spatial derivative of the deformations. Well, yeah, here. So I mean, isn't it? Yeah. So I mean, I think when you take the integrand, then it should be independent of the metric, or should be invariant under the redefinitions of the metric already, isn't it?
But we want to know how action change as a function of deformation of local metric, right? So we want to see integrand. You don't.
Yeah.
Well, yeah. Okay. Yeah. Anyway, this was a side remark, so maybe I had to simplify it. But anyway, the question I had was different. So is there any reason to consider this specific action where you just have one elasticity tetrad coupled to the two vector potentials and say not the other way around? So what dictates the choice? So it's actually the same thing for the 2D. Why only consider Chern-Simons action with vector potentials and not a combination of the vector potential and the tetrad or just the tetrad?
It's a great question. I will actually partially answer that question in the next slide. So
okay.
Yeah. Once we kind of construct different types of actions, I mean they correspond to different responses. That's
okay.
Yeah. Okay, but yeah. So the point was here that sort of once you construct the action this way, you get a scalar action. it does the topological invariance. In this case, the relevant topological invariants are described in terms of this sort of integrals over the area in the Brillouin zone. And okay, so the derivative of the vector potential is essentially the electric field, and the current you get basically from sort of vector potential derivatives of the action. It's not that straightforward, but roughly. But once you calculate the conductivity here, what you get is basically this law here. So the derivative of the conductivity with respect to the elasticity tensor is now proportional to let's say if you take the derivative with respect to the elasticity tetrad in direction A, you get this sort of integer NA here. Or let's say if you integrate, you get essentially this law here, where you sum over all repeating indices. So this is basically the generalization of this Halperin's law before. So you have this extra reciprocal lattice constant here, but this is also valid for weak deformations. So the question is, for example, how would be the quantum Hall response in weakly deformed media in the center? So it would be described by this. Okay, this was the 3D quantum Hall effect, and then I try to partially answer this Alexei's question once you consider another type of action. And now let's say you could sort of replace this vector potential term here by an elasticity tetrad field, and this is what I did here. Okay, and again I have a term that scales like 1 over L the fourth, but now the relevant topological charges are slightly different. Now the charge that goes here consists of an sort of 1D integral, so that now let's say the NZ, for example, for orthorhombic lattice, in this case the integral would go just along a line here, and this action does not describe quantum Hall response, but actually describes this polarization response. So from for an orthorhombic lattice, you can write this action in terms of this, where let's assume that there is only one topological charge. Then the action is basically the product between the electric field and the area that you obtain once you take this sort of cross product between the two elasticity tetrads. Okay, and the polarization is basically the electric field derivative of this term, and so which means that now instead of the quantum Hall conductivity, you get a surface polarization that is proportional to those topological charges. So it's a slightly different topological charge. It's a different response, and there are some subtleties. This polarization does not arise there spontaneously. You need actually have to have a small electric field in order to create it. So it's actually a jump in polarization that you are describing here, but this jump is quantized. Okay, I will show this in detail in a moment, so it becomes more clear. But basically the point is that you can get this notion of quantized polarization simply from the consideration of the possible topological actions with this elasticity tetrads. Alexei, did you still have a question, or? Because you have a hand raised.
No, I think.
Okay.
No.
Okay. Yes. There are also other types of actions that you can construct which contain a different number of fields. They also correspond to different physics. They are described in this paper, but I will not go into that detail. So here in the next part of my talk, I will try to concentrate on realization of this topological polarization, quantum Hall effect. The topological insulator with topological polarization. But kind of remind you that there are these two types of topological insulators that you can identify for crystalline matter in 3D. One with quantum Hall effect and one with quantized polarization jump. And they also correspond to different types of surface modes. So this case you would have this half Dirac surface modes, and in this case there's actually a flat band or drumhead surface mode states in the topological insulator. Okay, so kind of what I try to do next is to start from this picture of Dirac lines and then deform the model in such a way that I get this topological insulator with this spontaneous polarization or this quantized polarization jump. Okay, and I do it by starting from the honeycomb lattice. Okay, so I talk about honeycomb lattice because it's not graphene, because what I will do with it is something that you might not be able to do with graphene. But in general, what we know is that the honeycomb lattice, which has an AB symmetry, is a semi-metal. So it doesn't have to be carbon sort of lattice. But this semi-metal has these sort of pairs of valleys at which we have the Dirac points. Okay, now we want to make a 3D system out of this, and what we do is that we do it by stacking. And we do the so-called Bernal stacking of what also happens in graphene, but which we could assume to happen in this system. So we take sort of every pair of honeycomb lattices and we stack them on this AB stacking where we shift this lattice like this, where we then notice that sort of some of the atoms are on top of each other and some of the atoms are on top of the hexagon. And then these atoms on top of each other are bound to have a stronger coupling between the lattices. Now Alexei has probably a question.
Yeah, I'm just curious. You can also make a generalization of the you can also make a 3D lattice where every side has three neighbors, some weird looking brickwork lattice. So would that also work here, or stacking is just easier?
That's a good question. I don't know. We can discuss it. Let's discuss it at the end.
Okay.
I saw one. I mean, I happen to know this model, and therefore I show it. Anyway, so if you start doing this AB stacking, what you realize quickly is that you can actually then decide what you do with the next layer. I mean, always. So you can either do kind of so that this line of strongest couplings is straight, or that it's kind of a zigzag line where it's alternating. So every second sort of strongest line goes to a different place. And these two stacking sequences are called Bernal and rhombohedral, or AB and ABC for graphite. And they come up with slightly different topological structures. So this Bernal graphite or Bernal stacking they are both nodal line semimetals phases for weak coupling. In the Bernal case, you have these nodal lines are straight lines here in the lowest order approximation, whereas in rhombohedral they are this kind of spiral lines. And so one way to describe this system is to kind of see what happens starting from the kind of weak interlayer coupling. So we kind of assume that we can describe, firstly assume that we can describe the systems with just sort of this Dirac point picture on every layer. So we have sort of the unit cell contains in every layer sort of blue and red atoms, which are the same atoms, but I mean, but you still have two of them. And then sort of once we have the stacking, the rhomboidal stacking now stacks always the blue atom to red atom, blue atom to red atom, and so on, whereas the Bernal goes this way, zigzag. And you can quickly see from this picture that the unit cell of these two lattices is different. In the rhomboidal case, it's just one layer. In the Bernal case, it's two layers. And okay, and I will concentrate on this rhomboidal because it's like somewhat more interesting. One thing that you notice quickly is that sort of if you make a finite system, you always have these uncoupled sides at the end. So, and this actually is a source of the surface states of these uncoupled sides. So you can study kind of the low energy spectra, and indeed this sort of uncoupled sides actually at finite transverse momentum they do couple, and actually the coupling energy shows up as the sort of finite dispersion of these surface states. But the coupling becomes smaller and smaller. The coupling energy becomes smaller and smaller as you increase the number of layers, and eventually get a flat band for large n. The size of this flat band is indeed, it's the size of this interlayer coupling gamma 1 divided by the Fermi velocity of the individual sort of layers. Yeah, so to see what is actually happening, why is there's surface state, you start from the bulk Hamiltonian of rhomboidal graphite, which is pretty simple in the case of this, if you only include the strongest coupling. So you have the it's of this form where you just have these off-diagonal terms, and where this f function here consists of the intralayer term, which is just a Dirac point term, and then the interlayer coupling gamma 1, and then there's the exponent which comes from the 3D system. And then you basically find the zeros of the determinant of this Hamiltonian, and those zeros correspond to sort of points of degeneracy. And what you find out is that these points actually are at the point where the transverse momentum, the size of the transverse momentum is equal to this gamma 1 divided by VF, and the phase, the direction of the transverse momentum equals this pz times a, and this is nothing but a spiral. And now for the two valleys, you have actually spirals with opposite helicities, and this helicity can be thought to be a topological charge of this nodal line material. So this is a line because you have indeed sort of one parameter, which is basically you can choose pz to vary, and then once you do that, everything else sort of is settled for this line. Yeah. So now I told you that the size of the flat band is actually gamma 1 divided by VF, but now actually we know also how VF depends on this sort of intralayer coupling gamma 0, which is the coupling between nearest neighbor coupling between the lattice points in the honeycomb lattice. And what we find out is basically then that the flat band size is let's say the 1 over a squared, which is the microscopic scale in the lattice. This is the sort of honeycomb lattice constant, and then times the ratio between inter and inter. Sorry, this should be intralayer hopping, and this is typically much more than 1. Okay, and the picture is kind of this. We have these spirals, indeed, which are whose width is this gamma 1, and whose distance is governed by this gamma 0 parameter, the honeycomb lattice intralayer coupling. Okay, in the following, I will want to kind of make a point first about different types of nodal lines. So strictly now, when we talk about nodal lines, these are these lines of band crossings in the Brillouin zone. And actually, this should be 4D toruses, but I wasn't able to draw them, so I drew 3D only. So this is kind of the surface of this torus is the 3D Brillouin zone, and then sort of what we find out is that there are lines going around the Brillouin zone, which are these band crossing lines. And we notice that there can be two types of such lines. There can be lines where you just have circles inside the Brillouin zone, or you have the lines which go around the Brillouin zone, like this. And these correspond to different types of Dirac lines. And we call these lines are type A lines, and these are type B Dirac lines. Okay. And you can immediately notice that there is some difference in the robustness of these lines, because these type A lines you can deform by changing parameters. You can deform continuously into a point and then make them vanish. And they also are not independent; they are kind of independent of each other. So you don't necessarily have to actually have two such circles in your Brillouin zone. Only one is enough. Whereas here, you cannot deform them into a point, and they actually have to appear as pairs. So if there is a red line, there has to be a blue line, so to say. So the red and blue correspond to the opposite topological charges. Okay, well, anyway, so whenever you have these Dirac lines, you might have surface states which are essentially drumhead states or approximate flat band states at the surface. In the case of rhomboidal graphite, actually, the one can also go beyond this strongest coupling description. So one can add from, I mean, I included kind of gamma 0 and gamma 1, but you can also add gamma 2, gamma 3, gamma 4, and so on couplings, and then you get the full spectrum. But these are typically smaller, these other couplings, and they don't destroy the property that I'm describing. What they will just do is that instead of flat bands, they will promote the surface states to these drumheads, which have a finite dispersion. And but nevertheless, there are some symmetries that still protect this presence of this Dirac line. It just becomes a non-equi-energy line. There's a line of band crossings, but they are not at the same energy. And you can study what happens to the surface dispersion, and you see that it's not exactly flat anymore, but it's a bit sort of there's a quadratic contribution to it, but it's still a surface state. Okay, these are just examples of calculations for that. But in the following, I will just forget about these higher order hoppings, and I will just call this gamma 1, gamma 0 model. And I hope that this picture, I mean, it looks a bit complicated, but it's kind of, I try to explain it a bit. So, okay, there's a question.
Yeah. So in this case, this topological charge N1 is labeled with 1 and -1, but it looks like this system has inversion and time reversal symmetry. So I guess it is a G2 number, so there is no sign, right?
This Q here in this
that's G2 number
has no sign. That's true.
Okay.
The N, which is the chirality of the I mean the spiral, that can have a sign.
Also, N and Q is different.
And yes, they are slightly different, but indeed you are right that actually the sort of, if you just took what sort of response wise, these are the same. But there is a property kind of which is related to the Nielsen-Ninomiya theorem that they kind of have to appear as pairs. So in this sense, you have to consider them as opposite signs. Okay,
then what defines N1 then?
So
how do you define
this is okay. So you can don't think I have now let's see. It's basically the spiral helicity. I don't have the formula right here. Sorry for that, but it's I mean, you define you can also actually use the Hamiltonian to define the helicity, but the main point is that at the k and k prime points you have plus or minus phi here. So at different points you have a different sign of this phi, okay. And so, therefore you can have a different. And
does that mean if you make a blue spider and another blue spider close to each other, they cannot pair annihilate because of the N1 charge?
Yeah, I think that's what I'm claiming. Yes.
Okay, thank you.
Yes. Yeah, and exactly I'm getting actually there. So I want to start from this picture, and I try to explain this picture a bit sort of maybe it's clear, but to at least some of you, but it's not the best type of picture. Let's see. So what I have plotted here is first the first Brillouin zone of graphene. So the different points, if you just kind of look at the at the ky kx plane here, the different points here and there and so on are just the k and k prime points of graphene. Now, if you add the third dimension, you extend these points to lines in the third dimension, and then they connect from k prime to h prime and k to h points. Let's say here. Now, the question is what happens to the Dirac line? So let's first assume that the gamma 1 would be 0. So then we would just have a zero, sort of the Dirac crossing would be basically on this line because nothing would depend on pz. Okay. Now, if you have a finite gamma 1, what you do is that you sort of get this spiral, and the spirals have these opposite helicities at different k and k prime points. And okay, and then the projection of the spirals to the surface, they contain these flat bands, which are kind of denoted here. In the following, I want to just, okay, since I'm a theorist, I'm allowed to change parameters. So I will just change gamma 1 with respect to gamma 0 and see what happens. So, and there was kind of some hint about this already. So here is kind of the sequence of what I do is that I just increase this ratio of gamma 1 and gamma 0. So at first, for small gamma 1, I have these small spirals and the small flat bands on the surfaces. Now I increase gamma 1 and I increase the spirals, and I start to have this sort of flat bands become larger. They also actually become triangular because of this triangular warping in honeycomb lattices. And at gamma 1 equals gamma 0, they touch each other, these red and blue lines. And then beyond this touching, they actually cut each other. So, and then actually we get a Dirac line, which is only inside this Brillouin. So here, this Dirac line is this type B line, which goes around the Brillouin zone, whereas this is a type A line, which is inside the Brillouin zone. Once I increase gamma 1 further, so this Dirac line becomes smaller and smaller until at gamma 1 equals 3 gamma 0, it goes into a point, and then for larger gamma 1s, actually, it disappears. So there's a gap forming. If I look at the flat bands, so in here, the flat bands were small, they were increasing. Further increasing, and actually here the flat bands are the regions which are outside this projection of this Dirac line here. So, once I increase further, this region of flat bands actually increases even further, and then until it spans the entire Brillouin zone here. It's a bit easier to write here. So here is now indeed the Z2 charge that was mentioned here. So where you define the charge based on this Hamiltonian, and what you can see is that in this for the small coupling, this Z2 charge is finite for this sort of range of transverse momenta, but 0 everywhere else. Once I increase gamma 1, they become larger, these values which have a finite Z2 charge, which correspond then to the flat band surface states. And then once sort of this is already for very large gamma 1, these flat bands become larger and larger, and suddenly finally in this regime of gamma 1 equals 3, gamma 0, I get this topological insulator which has a flat band surface state. So it's an insulating state which has a flat band. Now I seem to have lost the battery of my mouse, so sorry, so I cannot point anymore. But let me fix it quickly. Now we want to study this polarization response of this system. So, but actually I simplified my model a bit for this polarization response. So instead of this honeycomb lattice, I just consider kind of similar Hamiltonian, but now I just change the px and py to sine px and sine py terms. And in such a model, this t is the parameter resembling the ratio of gamma 1 and gamma 0, and in such a way that there is this spiral phase, nodal line space at t smaller than 1. At t equal to 1, these spirals, they cut each other, and then they become this type A Dirac lines. And then at t equal to square root 2, we get the topological insulator phase. These are the corresponding spectra. Now, what I can do is to, okay, now remember that there should be this topological insulators with polarization jump. So I want to describe now the charge polarization in this system. So there is a way I can just calculate the eigenfunctions, eigenstates, and from the eigenstates calculate the charge density, and then from charge density I can calculate the polarization, which is basically a dipole field in this system. And I can do it by assuming an electric field in the system, which means that there is a chemical potential that depends on position in a certain way. Okay, and I neglect screening of this electric field. There is a parameter describing screening, which I then can just assume to be such that there is no screening. Okay, and now again the question is what provides the kind of the L. So because now here the charge density is of course E over L squared, and it should be sort of there should be some topological features to it. So E is just a natural constant, but L has to come from the lattice. Okay, now charge density, sort of this is actually charge density now as a function of the site index for a finite size system. So in this case it's 21 layers. I can go larger if needed, but basically what I found out is that the charge density becomes finite at the edges because of the surface flat bands, and it's 0 everywhere else. And the size of this charge density depends on sort of on my hopping parameter. So so here I just put some electric field. Now this charge density does not tell us how much, but actually this polarization tells quite a bit. So I calculate this polarization dipole, and I can do this as a function of the electric field that I put into the system. So, and what I find out is that it's because now in the system the flat bands are ideal. If I put a tiny positive chemical potential to let's say one side and negative in the other, which corresponds to let's say positive electric field, I completely polarize the system. Okay, and okay, so therefore there is this polarization jump in the system. So okay, and what I find out is that the size of this jump depends on this parameter t in the following way. So I start. So this is the sort of polarization jump in the nodal line phase. It increases as I increase t, and it's and whereas in the sort of topological insulator phase, it goes to a constant. It's not exactly 1/2 here. It should be 1/2, but it's not exactly 1/2 because of finite size effects. If I would just increase to a larger lattice, this would become larger here. The point is that in this system, because of the surface flat bands, this jump sort of between positive and negative electric fields is equal to unity in the sort of correct scale of the matter, and the scale is given by this S12. So the area in the transverse Brillouin zone, which, by the way, is the same as the size of the flat bands. So this is actually this polarization jump is just mimicking the sort of the increase in the flat band size in this system. Okay, so this is basically the main result, and I realize I already sort of by far exceeded my time, so I will just mention one thing, which is the last thing here, which is now the kind of aspect of chiral symmetry breaking. So my model was sort of in a way slightly unphysical because there was an extra chiral symmetry, in particular the Hamiltonian anticommutes with sigma z, and this is only approximate in sort of crystalline matter. In true crystals, there would be broken symmetry, and then instead of ideal flat bands, we would have drumhead states. So this I can sort of add to my system by adding a symmetry breaking term, and I indeed get this drumhead states. So they are not exactly flat. And what this does to the polarization jump is that it smoothens it. So instead of being this complete jump, it becomes smoother, but the size of the jump actually remains quantized. Okay. So in a way, this size of the jump is still a robust feature, even as long as this chiral symmetry breaking does not exceed the gap in the topological insulator state. Yeah, but also actually other effects would lead to a smoothening of this jump, like finite temperature screening. So I think the main feature is now the size of this step here. Okay, this is kind of the main result. So I kind of associate this topological response to surface flat bands, and it's quantized in the limit of topological insulators. So here, in the case of these nodal lines, there are flat bands. There is a polarization jump, but it's not quantized because it depends still on extra parameter, this t. But whereas here in the topological insulator phase, once this is saturated, it doesn't depend on any extra parameters anymore. But it's actually, well, it depends on this lattice parameter S12, but nothing else. Okay, I think I will skip the other part of my motivation, which is the minimizing delta E. If you wish to ask questions about it, I can answer. But this was about how to flatten bands with interaction. It's a slightly different topic, but I wanted to include it because of relation to recent experiments in twisted bilayer graphene. Okay, I came to my conclusions. As I noticed, 20 minutes late, sorry. So I hope I communicated this motivation for you. So to study flat bands, the interest in studying them in correlated matter, but in order to kind of satisfy increasing critical temperatures, increasing energy scales for these systems, you would like to increase the size of flat bands and also make them flatter. And one way to increase the size is to look for these topological insulator phases with quantized surface polarization. Okay, I thank you for your attention and great questions on the way.
Thank you, Professor Heikkilä, for this very interesting talk. Let us thank our speaker. And we have time for questions. So perhaps let me start. So this model that you've shown last, so you've started from graphite, right?
Yes.
And then you said you've kind of to make the calculation easier, you've modified it slightly. So
yeah.
Did you try also the kind of graphite model itself to calculate and compare? At least numerically, maybe, or
no, I didn't, but I basically know what would happen. So I mean, it is just a toy model to show sort of this physics, what this quantized polarization means. So you would basically have the same pictures as here, and the only difference is that the scale of this this would be different, because now this crossover happens at 3 instead of 1 square root 2. But that's basically all that would happen here in the case of graphite. Why we didn't do it in graphite was because well, I was doing all the numerics and it's a lack of time issue.
Mm-hmm. So for graphite, this has to do with changing the kind of tuning the hopping, right? The interlayer.
Yes.
Basically, so is it possible this to manipulate somehow experimentally, or?
Well, in principle, I mean, as a theorist, you would just think that you press the layers together, but of course, before you actually reach the topological insulator phase in this way, you are not you are going to destroy many other things probably on the way. So this here it's meant more as a sort of toy model system for kind of capturing this phenomenon.
What about maybe some other platforms to simulate maybe cold atoms or something else?
Yeah, definitely. Actually, I discussed part of this model already a few years ago, not the topological polarization, but the other part of the model a couple of years ago in to a group of people who are doing electric circuit type simulations of topological media, and they were going to go to 3D, and actually for them the larger interlayer coupling was an easier case. So indeed, there can be many artificial systems where you might have this physics.
And are you in contact? Maybe are they kind of working on this?
I don't know at the moment. Yeah, at least they were interested, but whether they really took it, I don't know.
Okay, thank you. We have a question or comment from Sung Jong. Please go ahead.
Thank you for the nice talk. I have a question about when you go from the strain to the what is that, some quantized effect or like some topology, is there any role of the induced polarization through piezo effect from the strain? Or is there any other interpretation of the same thing using not, I mean, you introduce some field, right? You introduce some like field, like you call the phase, right? And derivative of it. Is there any other like alternative way to interpret the same system using the piezoelectric effect?
It's a great question. I would guess that in order to get piezoelectricity on top of this, and this is just a guess, you probably need to have something that leads to a spontaneous symmetry breaking between these two polarization phases. So, which would be some kind of structural deformation, which would lead to, yeah, but in principle, I think the same action should, with the same action, it might be possible to describe piezoelectricity.
I see. I mean, for example, like for the case of the boron nitride, there is a very close relationship between the how can I say effective gauge field from the strain and the induced polarization.
Mm-hmm.
They are kind of like it's either one or the other way. So and one more question is like, I mean, so I guess the topological polarization you mentioned, there's nothing to do with the piezo effect, right?
That's kind of external. To do with what?
That's nothing to do with the piezo effect. This polarization is external, right? The quantized polarization you mentioned.
Yeah, it has nothing to do with the piezoelectric effect.
Okay. I see.
Yeah, so indeed, I think for piezoelectricity you would need to have some deformation that would break the symmetry, right? Mm-hmm. So in this sense, I think, I mean, if you would start from this action, but then you would allow for some, I mean, you would need something extra, some extra parameter that describe a symmetry broken system that would stabilize a symmetry broken system. Mm-hmm. And then you might get maybe a state without external electric field.
Okay, thank you.
Yeah. But this is guessing, so I
see. Okay. Mm-hmm.
Yeah.
Okay, do we have any other questions? Alexei, please go ahead.
Right, so that's the question I asked in the middle. So can you go please to the stacking slide?
Yeah.
Yeah, well, here, I recall the name of the lattice, the hyper honeycomb. So that's the 3D version of the honeycomb, which presumably has, if not all, at least many properties of the 2D honeycomb. I'm just curious, would these things work there? And that's basically the other half of the question is you consider two different types of stackings, but you can mix them. So what will happen if you now start making more complicated stackings?
Yeah,
so you can go like one Bernal, one rhomboedral stacking, and then repeat, or even go disordered, and it would still give.
Yes.
How would that? What kind of surface state that would lead to?
To make a periodic system and then a surface. That is a good question. We actually studied this long ago, so I answer first the second question because it's easier. We studied this long ago, but one thing that you know, at least, that if you have a maybe here, if you have a, let's say, Bernal stacking defect in a rhombohedral system. So what you would have, for example, here is that suddenly you would start to put these lines from, now they go from blue to red, but then here they would suddenly go from red to blue. Mm-hmm. Then you would notice that there is actually a localized state at the stacking fault itself.
Okay.
So you get actually extra flat bands which are at the stacking faults. So this would be the case when you have several rhombohedral stacked layers and then one Bernal stacking fault. now you are asking, what if you would have, let's say, a few rhombohedral and then Bernal, and then again a few rhombohedral and then Bernal, yes, so that you would kind of repeat this sequence. I guess I don't really know the answer to this. Actually, we started doing this indeed exactly towards that direction. It's a bit complicated technically to do the finite, let's say the finite layer sim, but not impossible. But I don't have the full answer to this. As for this hyper honeycomb lattice, I think the question is now then, can you create this? I mean, how would you create these nodal line faces? So like I said, in this rhombohedral stacking, you have the spirals, and then you can deform the spirals so that they cut each other and so on. This Bernal stacking, actually, this line can also be split, because actually the lines have a topological charge of 2 and -2. I mean, this kind of winding charge is 2. So, and then you can sort of split them into actually 4 lines, of 3 of them having a charge 1, and then 1 having a charge -1. And the distance is now controlled by the gamma 3 coupling, which is a bit smaller coupling. But in principle, then you could start to think what happens if you increase this coupling and sort of join those lines together. So that would be even more complicated system. But whether you get this topological insulator phase, I don't actually know. So there might be other roads to this topological insulator phase. That's basically what I'm saying. So we are just suggesting that one road there is via this sort of intermediate Dirac-Klein phase, but it is not the only necessary road.
Mm-hmm. Okay, thanks.
Thanks for the question.
Okay, do we have any other question from the audience? It seems not. So in this case, let us thank our speaker again. And thank you all for your attention. With this, we conclude our